here's the percent of cropland under different irrigation types. And you can see that it's about 44% pressurized irrigation, but that's always increasing. You know, pressurized irrigation includes drip and sprinkler. So you can see that in Nebraska, they have a lot of pressurized irrigation, Texas, California. This was in 1997. I pulled it out of my book, but you know, we only had 7% pressurized irrigation. And a lot of that was subsurface drip. The reason they didn't have center pivots is we have such a high evaporation rate, and the center pivots were designed with the sprinklers on top. And so they had like 50% loss in water before the droplets even reached the soil. So they tried them, and then it was just a disaster. And so they gave up on it. But then they reconfigured the center pivots to work in arid climates. And so we do have more and more center pivots all the time. So 94% of the irrigation in the world is surface irrigation. But in the United States, sprinkler irrigation is 46% of the irrigated acreage, and 75% of that is center pivots. So center pivots are by far the most popular sprinkler irrigation system. They're not tremendously efficient. Here they're in this range. Center pivots are the ones that go in circles. Linear moves are the same as center pivots, except they go in a straight line. But they have some advantages. You're irrigating a very large area, like 160 acres with one pipe, you know? So you're not installing all sorts of pipes in the field. You don't have to disturb the field because it's going around the field with tractor wheels. So it's the least expensive pressurized system by far, and it's the least expensive system to manage. For example, I talked to one farmer in Arizona, and he said that he had, I think, 640 acres, and he had one irrigator for every 160 acres, okay? And that was surface irrigation, like furrow or flood. Then he bought 4 center pivots. Oh, and he was also working like 16 hours a day managing his farm. Then he bought 4 center pivots. He was able to let all the irrigators go, and he only worked like 5 hours a day, you know, because the center pivots are all controlled by computer. And so in America, where we have high labor costs, center pivots are very attractive. They might not be quite as attractive in countries where there's labor that's very cheap, you know? So it's all part of an equation. There's capital costs, there's maintenance cost, there's, you know, management. So you consider all those things together when you're deciding what's the best irrigation system. But for the United States, center pivot is very attractive. There are some disadvantages. You lose production in the corners, but they do figure out ways to irrigate the corners. I used to work for an irrigation company, and one of the things our company did was install like permanent sprinklers in the corners. And you know what I mean by corners? Yeah. Okay. So there was this one farm up on the Horseheaven Hills in Washington State, and our company had installed the pipes at the typical distance between sprinklers and pipes, and they had like dry gaps in between the pipes where nothing grew, and that was because they had very high wind up there. So our company had to go back in and install pipes every other pipeline and just lose money on that. There's also infiltration problems. Like at the end of the pivot, the pivot's going very fast, so you have a very limited time to get the water into the soil. And as I said before, you might have evaporation problems. So that's some of the things we'll be talking about. This is a linear move. And so instead of pulling the water out of one pipe, you know, that the pivot is rotating around, with a linear move, you have to pull the water out of a canal. And that's much more problematic. You can imagine that your canal could have algae grow in it. And you also have a more complex system where you have the pump and its motor up on the pivot. You're pulling water up against gravity, so you could lose prime your pressure. That means lose prime. There's a lot of problems, but they are used in some places. So, and actually my PhD, I injected an oil-based pesticide into the center pivot pipeline. And then I went out in the cornfield and measured where it went. Because you can't just dissolve the chemical in the irrigation system, because then it's just going to wash off the crop. So if you dissolve it in an oil, then it's going to stick to the crop. And actually, I almost died, I think, because my gas mask wasn't working quite correctly. And I was spraying a nerve agent pesticide called Lorsban 4E, which I can't remember the name of it. It's a certain classification of pesticide. And I really started feeling, actually, I might be over dramatizing this, but I started feeling a little woozy. So anyway, I got out of there. But people do die from this pesticide. There was a pesticide applicator in Sacramento, which is near where I was working, and he crashed. And then all the nurses and all the doctors who rescued him died. You know, like 10 people died. So yeah, it's a little dangerous. Okay. Anyway, these are my papers. Haven't had the most papers in my career, but these are the papers we wrote from that. I did like modeling of how quickly the oil drops went up in the pipeline.
I was just curious, in this picture, are those solar panels on top of the?
Yeah.
Is that common?
No, it's not. I don't know why there are solar panels on this pivot. In fact, I don't think a solar panel could run one of these pivots. We had a huge motor on our pivot, like, you know, this big. So I don't see how these little solar panels would drive the pivot.
There's multiple components though, right? Like if you drive it.
Well, the motor was mostly driving the pump. But it's possible, you're right, that these solar panels are doing something. This is a USDA ARS picture, so it's probably an experimental linear move. So they're probably trying to do something. I wouldn't be surprised if you could drive the linear move if you had panels like extending a long ways on the pivot or on the linear move. Okay. So here's the original center pivots. So like I said, they started in Nebraska, and they had high pressure sprinklers on top because Nebraska is not that arid. So this is actually a big gun. So this would be what's on the end. And so what they're trying to do is take care of the corners by spraying the big gun in the corners. They also have linear moves that'll articulate into the corners. So they in order to take care of the corners. But like I said, this did not work in Arizona. They lost about 50% of their water from evaporation. So once they developed this kind of a system where you can either put the drop tube sprayers inside the canopy. So even this is going to have some evaporation because you know, it's spraying out, and then hitting the soil, but probably not very much. You know, it's all a function of how long it takes the droplet to reach the ground. So, and there's in the text, I listed several kinds of these. There's different kinds of these drop tube sprayers. There's MISA, LISA, LIPA, you know, depending on like exactly how much pressure they use, exactly, maybe they're even bubbling the water into the ground rather than spraying. So there's all sorts of options on that. And this is what they had way back when. They've improved them. They still use these, but what happens is the water sprays down and hits a plate and then spreads out. So we're going to do an evaporation example. It's example 12.1. And these experiments were actually done in Arizona. I can't remember what their names are, but they're in the text. But the amount of evaporation is a function of the drop size. And obviously, this is just an empirical equation based on regression of experimental data. So it's based on diameter of the sprinkler. ES minus EA is vapor pressure deficit. Do you know what ES and EA stand for?
Evaporation, soil evaporation, air.
No, a good guess.
Saturation.
Yes. ES is saturated vapor pressure, which is 100% relative humidity. And what's EA?
Atmospheric.
Atmospheric. Close. Actual. Yeah. So we're just looking at the difference between completely saturated air and the actual vapor pressure. And it's just like relative humidity is 40% or 60%. Relative humidity is 100% in a humid area, and maybe down to 10% in Arizona. So if your vapor pressure deficit is high, that means you have something like 10 or 30% relative humidity. If your vapor pressure deficit is low, then you would have like 90 or 100% relative humidity. So as far as equations go, I think it's easier to use. I haven't looked at this in detail, but I think it's easier to use vapor pressure deficit than relative humidity. It's more of a it's more fundamental. Okay, and then we have LE, which is our percent evaporation and wind drift. So they also include wind drift in here. You know, the wind can carry away the sprinkler droplets as well as just evaporation. And then we have the nozzle operating amount. But when you have high pressure, the flow breaks up. There's more turbulence and it breaks into droplets. If you don't have high pressure and it's spraying out at a low velocity, you don't have as much turbulence and it just sprays out as a stream, you know? So you don't want that. But anyway, that's why nozzle operating pressure is in this evaporation equation. The higher the pressure, the smaller the droplets coming out of the sprinkler. Okay, and then of course, wind velocities in there, carrying the droplets away, but probably also adding turbulence and resisting the movement of the droplets down to the ground. All right, so here's example 12.1. And so we're going to calculate the evaporation in Arizona, which would be the arid climate, and in some humid climate. Okay, so here's condition one, the arid climate. The relative humidity is 10%, so that's typical for Arizona. Temperature is 40 degrees centigrade. And the reason we need that, I didn't talk about it, it was on the slide, but your vapor pressure deficit is a function of temperature because the amount of water the air will hold is a function of temperature. That's why your relative humidity goes up and down. When it gets cold at night, what does your relative humidity do?
It drops.
No, it goes up.
Relative humidity goes up.
Yeah, because you have the same amount of water in the air, but the air will hold less water. So yeah, so that's why you see your relative humidity go up at night and down in the daytime. It's the same amount of water. Okay, so our temperature is 40 degrees. Our diameter of our nozzle is 9/64 inch, which is 3.57 millimeters. And our wind speed is 16 kilometers per hour, or 4.44 meters per second. And our pressure is 70 psi, which is very high. But, you know, when they used to have the center pivot nozzles on top of the pipeline, they might run them at 70 psi. That's a little high for a typical impact sprinkler, but it's not out of the, you know, it's within the operating range. And that would spray your sprinkler water farther, okay, away from the pivot. And can you think of the advantage of doing that, spraying your sprinkler water farther away from the pivot?
Irrigate more?
Hmm?
You can irrigate farther?
Well, you can.
Go faster.
Yeah, you can go faster because your application time is a function of the diameter of spray and how fast the pivot's going. So at the outer end of the pivot, you can move the pivot faster because you're not going to exceed the infiltration rate if you have a wider application area. Good. Okay. So, and here's the humid climate. Relative humidity is 90%. Temperature is 25 degrees centigrade. Diameter is 9/64. Wind speed's 8. And again, H is 70. So we plug the equation in for arid climate. We first have to calculate the relative humidity, or the vapor pressure deficit. And we do that by calculating the saturated vapor pressure. And that's 0.61 times the exponent of 17.27 times 40, which is the temperature, over 40 plus 237.3. And remember, that's the Kelvin scale. So we're going to Kelvin scale there. And then the saturated vapor pressure is 1, and we're subtracting 0.1, which is the actual vapor pressure. It's 10% of 1, okay? Because it's 10% relative humidity over here. So our vapor pressure deficit is 6.63 kPascals, and that's how it's typically reported as a pressure, kPascals. Okay, so then we can calculate our fraction of evaporation. So we have 1.98 times 3.57. And I forgot what 3.57 is. Let's look.
It's the diameter.
Okay, yeah, the nozzle diameter in millimeters, right? And then we have 0.22 times our vapor pressure deficit. We have 3.6 times 490, which I think is our operating pressure in kPascals. Oh, thank you.
Oh no, yeah. Well, H is not height. It is nozzle operating pressure. Sorry.
Yeah. Okay, so 70 psi is 490 kPascals. And by the way, this is one of the problems we have in irrigation engineering. All farmers operate in English units, and all scientists operate in metric units. So pretty much have to report both. Okay, and then 4.44 is what? Oh, wind velocity, thank you. So we have 39% evaporation. That's before the water even hits the soil in Arizona. Okay, and then in our humid climate, I won't go through all the numbers, but the evaporation percentage is 7.6%. We calculate the flow rate of the center pivot as the application rate, gross application rate. So that's before the evaporation, the area of the pivot, and then 1 minus the fraction of downtime. So we need a application rate, an overall application rate for the pivot. And what would that depend on? What do we need to keep up with when we're irrigating?
Pressure? Does that have to do with pressure?
Not really.
What was the question? What we have to?
What would determine the overall application rate of the pivot to the land? What are we trying to keep up with? Well, that's going to be, we're not trying to keep up with infiltration. We're trying to keep infiltration down, infiltration rate down.
Runoff. Runoff water.
No?
The evapotranspiration of the crop.
Yes. Well, here's our 455 student. We're trying to keep the crop irrigated, you know, so that's what's driving all in all of our applications, center pivot, surface, drip. We're just trying to keep the crop happy. So this is in chapter 2, but as an irrigation engineer, I had to memorize 2 things. I had to memorize the required crop evaporation, and I had to memorize how to figure out how much pump flow we had. So, right. So that's what's going to drive IG. And so let's go to example 12.2 now. And we'll look at this calculation. So the area is pi times r squared max, or the maximum diameter of the center pivot. And then we have a conversion factor, which is, there's 1 hectare over 10,000 square meters. So we have our length of our pivot. This is a typical length, 400 meters, a radius center pivot. And then we can convert that to hectares. Okay. Our required application rate, so this is keeping up with the crop, is 16 millimeters per day. In Arizona, crops typically have an evapotranspiration requirement of about 13 millimeters per day. That would be like wheat, cotton, whatever, in the summer. That's based on the weather, but also on the crop needs. So every crop, you know, crops don't have the same amount of evapotranspiration requirement. For example, we've been working with Waiuli, which is a desert plant, and it has a lower lower requirement than, let's say, wheat, or you can imagine that orange trees would have a very high evapotranspiration requirement. So, okay, so 16.2 millimeters per day, 50.3 hectares. And then when we design a center pivot, we have to figure that it's going to be down part of the time. You know, all those wheels and gears and stuff are not going to work all the time. The pump might need to be serviced. So we're going to design it for being down 2 out of every 24 hours. And then we have this conversion factor here, 0.116. So our center pivot is going to have a flow rate of 103 liters per second. Okay. And so I made this spreadsheet here. Go ahead and open your spreadsheet. And so we said the pivot length was, so there's different sections of the spreadsheet that you'll use for different reasons. And so we're using this little section here to make this calculation. So our center pivot is 400 meters long. That means our pivot area. So the yellow ones are the calculated values and the white ones are what you need to input. Our hours per day operation would be what? And I don't think you can probably see this, right? Okay, what's our hours per day of operation?
22.
Yeah, 22, because we have 2 hours downtime. And our gross application required is 16 millimeters per day. So our liters per second is 102 liters. I think the book says 103. And our normal gross application rate on a 24-hour basis, so if we left it on all the time, it'd be 7.5 millimeters per day instead of 16. Okay. So, okay. So that's all these calculations you can do in this spreadsheet. Any questions on the spreadsheet? All right, so we did the first thing we needed to do. We designed the flow rate for the center pivot, not based on it, so not based on any sprinklers, just based on the field area that's being irrigated, we could calculate the flow rate required. Although we would have already had to calculate the crop evapotranspiration demand plus the LE, the fraction evaporation. So both of those would be in that gross application rate. Okay, so we did that. Now we're going to calculate the time of application. So like I said, this is a function of how fast the center pivot is moving and the radius or the diameter that's wetted. Okay, so obviously if it's moving at a certain rate, it's going to have a shorter application time than if it's moving at a slower rate. So our equation for the time of application at the end of the pivot, that's where we're concerned because that's where it's moving the fastest. Our time of application would be the time for one complete rotation of the pivot. And actually in Arizona, some people like have the pivot go around 3 times a day. And the reason for that is they want to put on less water for each application so that you can use surface storage to store the water while the water infiltrates. So that's kind of counterintuitive that you'd make it go faster in order to not have runoff, but that's taking advantage of surface storage. Okay, so we have the sprinkler wetted diameter, and then we have the radius of the center pivot. So let's look at example 12.3 now. Okay, so here's example 12.3. For this pivot, it's going around it once a day, so it's 24 hours. The diameter, the wetted diameter is 4 meters. So this would be, something like this, spraying out 2 meters on each side. And we have the radius of the pivot, 400. So we have 2.29 sprinkler application time. So let's go to our spreadsheet. So here, our sprinkler distance is 400, I think. Our wetter diameter is 2 meters. Our rotation rate is 24.
4 meters, the way down.
Oh, is that what it says? Okay.
Yeah. Yeah.
Okay, so our sprinkler application time is 2.3 minutes. That means from the time the water reaches a certain point in the field to the time that the sprinkler leaves that point in the field is 2.3 minutes. So we have to infiltrate all our water or use surface storage during that amount of time. We cannot have runoff. We do not want runoff. Because one of the advantages of pressurized irrigation is that you're applying the same amount of water to all parts of the field, or at least supposedly. So now that we know the application time, we can figure out the maximum application rate because we know the total application that we have to apply, okay? And actually, the application rate is approximately an ellipse, okay? And so we have an application rate of 0 before the sprinkler gets there, and then we have an application rate of 0 at 2.3 minutes, which is when the application rate ends. But then this is our maximum application rate. And so I don't expect you to go through all this, but I'll just review it. The equation for an ellipse is the position over the maximum. You know, an ellipse has 2 dimensions. So it's the position over the maximum in one dimension. So it has the application rate dimension, has the time dimension, and then it's the time over the total application time. Okay, so that's the fundamental equation, and then we're going to rearrange it. So I don't know if you can see here, but I've isolated di over dt by moving the other terms over to the other side and then taking the square root of that. And if you do some math, which we're not going to do today, we have this we have this result that the di over dt max equals 4 over pi times the daily application. So remember, we had the gross application was 16, but the daily application might be more like 13 because we're not including evaporation in the infiltration rate calculation because that's already gone by the time it hits the soil. So we have IA over TA, the total application time. And so I mentioned IA, that's IG, remember that was 16 times 1 minus LE, the fraction of evaporation. Okay, so we can calculate that di over dt max in the spreadsheet by using this equation. So let's go to the spreadsheet. So this is over to the right. And remember, our fraction of evaporation was 0.11. So our max application rate should be 8.63 millimeters per minute. So that would be this, okay? So this is our application rate versus time. And when the sprinkler's right over the top of the point, the application rate is 8.63 millimeters per minute. Okay. Were you all able to get your spreadsheet working? All right. Make sure you work on it because and then it'll be easier later. Okay, so we did example 12.4. Now, here's the very interesting graph. Infiltration rate is the amount of water the soil will take in, okay? So when the soil's dry, it's going to take in a lot of water, as you can imagine, due to capillary action and also due to gravity pulling it down into the soil. And then once the soil starts filling with water, the infiltration rate is going to decrease. So for every soil, we have sort of an infiltration rate curve. Of course, it's going to be different based on the antecedent moisture conditions. So this is a mature corn crop. And so we're not losing surface evaporation from the corn crop. Of course, with this system where we're spraying off the top and we don't have drop tubes, we're losing water when it hits the corn and sticks to the corn and then it evaporates, okay? So there's really no way to win here. But if we had drop tubes going down into the corn and just spraying the water on the ground, we wouldn't be losing water to evaporation, nor would we be losing evaporation from the soil surface between center pivot passes. Okay, well, when infiltration or when application exceeds infiltration, as here, so all this is excess water, you know, the soil can't take all this water in, then we have runoff, and then we lose all of our advantage of the center pivot system. So this is the difficulty of designing center pivots and why it depends on the soil type even, you know, so the center pivot companies, they have advanced programs to design their center pivots where they design like every nozzle flow rate and so on. And the real constraint is this infiltration rate of the soil. They can't have a sprinkler application rate that exceeds that infiltration rate of the soil at the end of the pivot, or they'll have this. Anyway, what the Soil Conservation Service has done is they have, and now they're called the Natural Resource Conservation Service. And actually, this is used by both civil engineers and agricultural engineers and soil scientists. They have classified soils, you know, like a clay soil would have a low intake, a sandy soil would have a high intake, okay? And so the form of this equation is I equals AT to the B. Okay, so that's the Soil Conservation Service format of the Kostiakov equation. And they also add a C for like cracks or whatever, instantaneous infiltration. So, and that's always 0.6985. That's why it's not in this table. And they have 1A for centimeters and 1A for inches. The exponent is always the same. So, and this is used in like civil engineering calculations of runoff from watersheds. You know, they have what are called intake families. And so in the spreadsheet, we also have intake families where you can specify an intake family, and the intake family here has a certain A and B associated with it. That's why the intake family is in white. That's what you specify. And the A and B are calculated based on the intake family. So if we change this to 2, hopefully it'll change. Yeah. So if we change it to 2, intake family 2, which might be a sandy loam or something, we have a certain A and B. And we can also specify the surface storage. So every time we go around the field, based on the characteristics of the soil and the crop, we know that we can store a certain amount of water. For instance, I think I have it in here. Yeah, I have it in the book. Yeah. So here's an alfalfa field that they're irrigating with a sprayer right down by the crop. So there's almost no evaporation. And you can see that the crop, even though it's a level field, although there's some undulation, the crop is sort of preventing the water from running off before it infiltrates. So that's where you'd have, you might specify some surface storage. Okay. So if we go back to the spreadsheet, then we have our intake family here. And then we have our infiltration rate curve here. And the reason it's not on here is it hasn't been, I think I have to update it. Yeah. Yeah. So here, so I guess when the spreadsheet's just stored, it's not, doesn't have intake family. But you can see that if we had an intake family 1, then with this application rate, we would have big problems. Okay. So we should not do this. But if we had an intake family 4, well, it's still bad. But let's go over to here and look at our surface storage. Still, our runoff is 5.66. Okay, so this is not good. So we're going to have to change something. So let's have a wetted diameter of 8. Okay, now we have very little surface runoff. And let's increase our surface storage to 6. Okay, that doesn't change these curves. The surface storage is used in this calculation here of runoff. So if we had 6 millimeters of surface storage, that would account for this area here. And then we would have, let me increase the size. So if we had 6 millimeters of surface storage, even though we have some infiltration that's not going into the soil because the application rate is exceeding the infiltration rate, the surface storage is taking care of it. Okay, so you can see how you can play with this spreadsheet to try to get it to work. Okay, and were you all able to make your spreadsheets work? All right. And also, are you all aware that all the questions are in all the answers are in the large book? So I don't know how much of an advantage that is, but maybe if you don't want to look at it, I guess you don't have to.